All right, this is section 1.5, combinations of functions. Our objective today here is to compose and decompose functions. We'll start off with the basics. The sum, difference, and product of quotients. Sum, difference, product, and quotients. Given functions f and g, we can find that functions f plus g, f minus g, f times g, and f over g. Sorry, that got a little away from us. And those are defined by f plus g of x is f of x plus g of x. I just add them together. F minus g of x equals f of x minus g of x. F times g of x is f of x times g of x. And f divided by g of x is f of x divided by g of x, provided g of x is not equal to 0. Remember, your denominator can never be 0. The domains of the functions f plus g, f minus g, f times g, and f divided by g are all real numbers in the intersection of the domains of the individual functions f and g, so whatever they have in common. For f divided by g, we further have to restrict the domain to exclude the values of x for which g of x equals 0. So we have to limit it a little bit more. So let's evaluate these functions. I have n minus m of negative 6. That means I can take n of negative 6 minus m of negative 6. And I can easily find n of negative 6. N is absolute value of x minus 3. So absolute value of negative 6 minus 3 is the absolute value of negative 9, which is just 9. Plop that in there. Then I can also find m of negative 6, which is 4 times negative 6, which is negative 24. Here I have 9 minus negative 24, which we change into 9 plus positive 24, which makes 33. For our next one, we're going to do n times p of 1. Well, just like before, with the adding, I can take n of 1 times p of 1. So let's find n of 1. The absolute value of 1 minus 3. Well, that's the absolute value of negative 2, which is just 2. And p of 1, which is 1 over 1 plus 1, which is 1 over 2. So we have 2 times 1 over 2, which is just 1. Now I'm asking for p slash m of 0. Remember, that means divided by. So I can just find p of 0 divided by m of 0, as long as m of 0 isn't 0. So let's find p of 0. So p of 0, 1 over 0 plus 1, which is 1 over 1, or just 1. So we have 1 over m of 0 is 4 times 0, which is 0. So we got 1 over 0. Remember, dividing by 0 is never allowed. This is undefined. No solution here. And for m minus p of 2, we do the same thing again. We're going to take m of 2 minus p of 2. Well, m of 2 is 4 times 2, which is 8. And p of 2 is 1 over 2 plus 1, which is 1/3. So I have 8 minus 1/3. Well, in terms of thirds, 8 is 24 thirds. 24 thirds minus 1/3 is 23 thirds for our final answer. Now we're going to do the same thing, but we're going to use x's. We're not going to actually plug in a number for x. And then we're going to write the domain in interval notation. So n minus m of x. We just take n of x minus m of x. Well, n of x, it says right here, is x squared minus 9. I'm going to subtract m of x, which is x plus 3. Now I just have to simplify this. I'll distribute my subtraction, x squared minus 9 minus x minus 3, and then write it in standard form, x squared minus x minus 12. We also have to state our domain. Well, the domain of n is all real numbers. The domain of m is all real numbers. So the domain of their subtraction is all real numbers, which is negative infinity to positive infinity. For m times p of x, we're going to take m of x, and we're going to multiply by p of x. There we go. M of x is x plus 3. P of x is the square root of x plus 1. Now there's really no simplifying that I can do here. I can distribute the square root of x plus 1 and make it x times the square root of x plus 1 plus 3 times the square root of x plus 1. But I don't know if that's necessarily simpler, so I would probably leave it right here. Now for our domain. Well, the domain of m of x is all real numbers. The domain of p of x, remember we have to take x plus 1 is greater than or equal to 0. So x has to be greater than or equal to negative 1. So what those have in common, all real numbers and x being greater than or equal to negative 1, is that x has to be greater than or equal to negative 1. So that means our domain is negative 1 to infinity with a bracket on the negative 1. And now p divided by n of x. To simplify this, we're going to take p of x over n of x. Well, p of x is the square root of x plus 1. N of x is x squared minus 9. We can't simplify that at all, so we just go straight into our domain. In the last problem, we said that x had to be greater than or equal to negative 1 for p. We have the added piece of making sure the denominator does not equal 0. So x squared minus 9 cannot be 0. Add the 9 over, x squared cannot be 9, which means x cannot be positive or negative 3. Well, negative 3 doesn't fit into x is greater than or equal to negative 1, so I ignore it. Now to write this domain, it gets a little tricky. What I'm saying is I can start at negative 1 with a bracket, and I go until I hit this issue at 3 with a parenthesis, or on the other side of 3, I can go on forever. So it's similar to our domain from the last problem, except that we have that little extra issue at 3. And for m minus n of x, I'm going to take m of x minus n of x. M of x is x plus 3. N of x is x squared minus 9. I'm going to distribute that minus 9. So I'll get negative x squared plus x plus 12. This is very similar to the first one, except you'll notice that all the signs are changed to n minus m of x. And our domain here, just like the very first one we did in this problem, negative infinity to positive infinity. Now we're going to talk about composition of functions. The composition of functions f and g is denoted with f, a little o of g, and it's defined by f of g of x equals f of g of x. Basically, it means I take g of x and I plug it into f. The domain of f of g of x is the set of real numbers, x, in the domain of g, such that g of x is in the domain of f. So we have to do a kind of thing within a thing here. We're going to start with g, figure out its domain. Then we also kind of have to figure out its range, because its range has to fit in the domain of f. So g has to fit inside of f. So given these two functions, we're going to find f of g of negative 4. When we do these problems, we always start on the inside, so we're going to find g of negative 4. So I take negative 4 minus 4, which is negative 8. Now I'm going to find f of that number, f of negative 8, which is negative 8 squared plus 2 times negative 8, which is 64 minus 16, which is 48. So that means f of g of negative 4 equals 48. For the second one, g of f of negative 5, the inner one here is the one that's listed second when we list it in this notation. So I want to find f of negative 5 first. So I'll take negative 5 squared plus 2 times negative 5, which is 25 minus 10, which is 15. Then we go to the outer function. I need g of what I just got, g of 15. So that'll be 15 minus 4, which is 11. So that means g of f of negative 5 is 11. So two different ways to write the same type of problem. Let's try a few more of these. F of 8. Well, I start on the inside with my f of 8. I get 8 squared plus 2 times 8, which is 64 plus 16, which is 80. Then I want f of what I just got there, f of 80. Well, I'm going to type this in my calculator. 80 squared plus 2 times 80 is 6,560. The next one is f of g of 9. We start on the inside, so we start with g of 9. G of 9 is, 9 minus 4, which is 5. Then I take my outer function, which is f, and I plug in what I just got, f of 5. 5 squared plus 2 times 5, it is 35. So, f of g of 9 is 35. Now that last one I forgot to write, f of 8, 6,560. And then g of 2. Start on the inside. G of negative 2 is negative 2 minus 4, which is negative 6. Then I go to my outer function, which is g again, and I plug in that negative 6. So I get negative 6 minus 4, which is negative 10. So g of negative 2 equals negative 10. All right, now we're going to switch to just using x's. F of x is 3x plus 4. G of x is 1 over x minus 1. We're going to find f of g of x. So this means that the second one is the inner function, g of x. I take g of x and I plug it into f in place of any x. So I'm going to take 3 times g of x plus 4. G of x is 1 over x minus 1. The only simplifying we can do is to make that 3 over x minus 1 plus 4. So f of g of x is 3 over x minus 1 plus 4. The domain, we have to think about what the domain of g of x is. Well, the domain of g of x is that x minus 1 can't be 0, so x couldn't be 1. The domain of f of x is all real numbers. So plugging g into f doesn't really change anything about the domain. So the domain is just that x can't equal 1. So to write that in interval notation, we write negative infinity to 1 or 1 to infinity. This time we wrote it in a different format, but it's the same problem. F of x is on the inside this time. So I take f of x and I plug it in to g of x. So I'm going to have 1 over something minus 1. That something is the 3x plus 4. So g of f of x is 1 over 3x plus 3. Now this time we want to think about our new function. What values in the range of f of x aren't in the domain of g of x? Well, those will be whatever make this new denominator 0. So 3x plus 3 cannot equal 0. 3x cannot equal negative 1. X cannot equal negative 1/3. So to write our domain in interval notation, we take negative infinity to negative 1/3 or negative 1/3 to infinity. No, we don't. I lost my mind there for a second. Subtract over my 3, I get negative 3 there. X doesn't equal negative 1. That throws off my entire domain. My domain is negative infinity to negative 1 or negative 1 to infinity. Sorry about that one. All right, I've got two new functions, f and g. I want g of f of x, and to write the domain in interval notation. My inner function is f, so that means f is going in to g. So I put 1 over, plug in my f function, square root of x minus 1 minus 3. And I can't simplify that at all. So that is g of f of x. To find the domain on this one, we'll actually look at the domains of each separate function. The domain of f of x is that x minus 1 has to be greater than or equal to 0, so x has to be greater than or equal to 1. The domain of g is that x can't be 3. But I don't care about the domain of g, I care about the domain of f that makes it so it's not in the range of g. So we're actually just going to take our new denominator and say that can't equal 0. Oops. Square root of x minus 1 minus 3 can't equal 0. So we add the 3, we get the square root of x plus minus 1 doesn't equal 3. We square both sides. We get x minus 1 doesn't equal 9. Add that 1, x can't equal 10. So x has to be greater than or equal to 1, but it also can't equal 10. So our domain is 1 to 10, or 10 to infinity. All right, now we're going to do a little application here. An artist shops online for tubes of watercolor paint. The cost is $16 for each 14 milliliter tube. We're going to start by writing a function representing the cost, C of x, in dollars for x tubes of paint. Well, cost of x tubes of paint is going to be $16 times x tubes of paint. There we go. There's a 5.5% sales tax on the cost of merchandise and a fixed cost of $4.99 for shipping. We're going to make a different function representing the total cost for A dollars spent in merchandise. So T of A, well, if I have to pay a 5.5% sales tax, that means I need to multiply my total by 1.055 times my total, which is A, plus that $4.99 I'm getting charged shipping. There's my function for T of A. Now we're going to find T of C of x and interpret its meaning. Well, T of C of x just means I plug C into my function T. So to get T of C of x, I need to take 1.055 times my function C of x plus $4.99. Well, C of x was 16x. And when I multiply that out, I get T of C of x equals 16.88x plus $4.99. The meaning in context. Well, if x is the tubes of paint and t is the total cost, this function represents the total cost for x tubes of paint. And when it says total cost, it means total cost counting shipping and everything. Now we're going to evaluate T of C of 18 and interpret its meaning. So to get T of C of 18, it might be easier at this point to just plug it into our new function, 16.88 times 18 plus $4.99. And we find that T of C of 18 is 308.83. So interpreting the meaning is that if I buy 18 tubes of paint, the total cost is $308.83. And finally, we need to practice some decomposing functions. We just compose them, but we also need to break them back apart. So what I'm looking for here is what would be the inside function. Well, inside of these parentheses, I see an x plus 1, two separate places. So our inside function we're calling g. So g of x is going to be x plus 1. Now I replace anywhere I saw that x plus 1 with an x when I switch to my outer function, which is f of x. So I call f of x x squared minus 3x plus 4. All right, another one. We have the square root of x cubed minus 1. Well, my inner function, inside I see an x cubed minus 1, so let's make our inner function, g of x, equal to x cubed minus 1. My outer function then, what is left when I take that out, I got a square root and I'm going to replace it all with an x. I get the square root of x. And finally, h of x equals x cubed plus 1 squared. What looks like it's on the inside? X cubed plus 1. So my g of x, my inner function, will be x cubed plus 1. If I replace that all with an x, what's left is my f of x, my outer function, which will be x squared.